Okay, sorry for the AV difficulties. Well, welcome everyone to RSS 2022. My name is Kris Hauser, and I'm the program chair. It's thrilling to see you all here in New York City in person, and this is my personal favorite robotics conference. No offense to ICRA, of course. I'm excited to see so many familiar faces in the room, and some of you are actually new here. So I want to just check for the show of hands. How many of you? For how many of you is this your first RSS conference? Wow. Okay, that is fantastic. I'm very excited to see so many new people here. This is a great conference, and I'd really like to show how fantastic this conference really is. We have. Okay, one other question. How many of you, for how many of you is this your first conference post-COVID? Wow, okay, not a lot of ICRA attendees here. Okay, great. Well, so you're in for a treat because we have a huge number of exciting events for you this week, and I would like to, well, I wish I had some AV here. All right, so let's see, let's go ahead and...
We come to this place for magic. We come to a conference to laugh, to cry, to care, because we need that, all of us. That indescribable feeling we get when the lights begin to dim and we learn something we've never known before, not just informed, but somehow reborn, together. Dazzling figures on a huge PowerPoint screen, proofs that I can feel. Somehow, heartbreak feels good in a place like this. Our academic heroes feel like the best part of us, and papers feel perfect and powerful. Because here, they are. RSS 2022. We make robotics better.
Thank you for that. If you don't get the joke, just Google Nicole Kidman AMC Theaters, and you'll hopefully get it. All right, so I want to say a few things about RSS. Sticking with the RSS tradition, we have a single-track conference, which is a fantastic way for all of you to see the best and the newest in robotics. We get a broad cross-section of robotics researchers, put them in the same room, and we share a common experience intellectually, socially, and culturally. With the conversations we have here, we get to collectively define what our field is, and we get to redefine where it's going. That's the feeling of collective culture that we've been missing so much during the pandemic. So let's see, let's go ahead and, oh, I got the clicker here. All right, I have a couple of bits of information for you before we start. Just for those of you who haven't seen this yet, our public information for those of you who are attending is up here at this attending site. Our Wi-Fi here is just the Columbia Public Wi-Fi network. No need to log into anything to log in, so very easy to get set up. For those of you who are watching online, we do have a Zoom session as well as a YouTube session that's broadcast for free. For those of you who are virtual participants watching out there, please log in to Feedloop, which is given by this site. You're given the stream to the webinar as well as the ability to ask questions and also type things in the chat. Please use the Q&A for questions. If you, during the Q&A sessions, we will be monitoring the Q&A in Feedloop on the Zoom room, and we will then relay those questions to the speakers up here. So for those of you who are online, in order to get all of the content, please log in through the channel as shown here on the slide. Some of you have already gone to workshops. Some of you will be sticking around for workshops. Oh, sorry, that's not this slide here. Okay, one other thing that I'll say, technical issue, is that oftentimes watching a Zoom session in the browser is not great. So if you do have some problems kind of logging on, click on the little bar at the bottom of the stream window and then open things up in your own Zoom browser. For those of you who require captions, we do have live captions available on the Zoom stream. We also do have a URL. If you click on this attending page, the URLs for each individual session are given, and you'll get a live transcript of the transcription going on now. All right, COVID policies. So for those of you who have not had COVID yet, congratulations. I did get COVID after ICRA, and many of my colleagues have as well. Even though if you're not worried about getting seriously sick, being sick for 1 or 2 weeks is no fun. My department chair is currently sick from COVID after catching it from ICRA. So please keep your masks on. This is Columbia University policy, and if you need a mask, we have them at the registration desk. If you are eating, drinking, or speaking, you may go ahead and remove those masks if you prefer. If you need to get help, whether it's directions or with your talk or your poster, you can either go and find a volunteer. They're in the white I Love RSS shirts. I guess that's I Robot RSS shirts. Or you can email our local arrangements chair, Matei Ciocarlie, the hardest working man in the room right now, and he'll respond quickly. He's not checking his email though right now, I see. So if there's any urgent issues involving safety, we have the Columbia helpline up here. You should call them on your phone. If you have questions on the virtual program's technical issues, please contact Brian Plancher through email here. All right. So we have a very exciting conference program for you. We have 74 papers, and we also, so 5 of them will be virtual, 69 of them are in person, and I am really thrilled that so many of you are so excited to come back to in-person conferences and actually come and present in person. We also have an exciting panel of keynote talks as well as early career spotlight talks. So we have Raquel Urtasun from University of Toronto and Wabi.ai, John Rogers from Northwestern University, Henny Edmoni from Carnegie Mellon University as our first early career speaker, and Jens Kover at TU Delft. A couple of bits of announcements. I'm going to steal some of Matei's thunder here, but we have a Thursday lunch tour of Columbia Robotics Labs. For those of you who are interested in taking a tour with those labs, please sign up at the registration desk. We have a limited number of slots available, but lunch will be provided during this tour. It is first come, first served, though, so please, after the coffee breaks, please feel free to go to the registration desk and sign up. I would like to give a big thanks to all of the sponsors for RSS. We had a number of sponsors, really excited to also see you all in person. They are, the Patreon level sponsors are Amazon Robotics, Dexterity, Raytheon Technologies, and Toyota Research Institute. So a big shout out to you guys. Let's give them all a round of applause. We also have our sponsor level sponsors, which are Mitsubishi Electric, Zoox, and Lockheed Martin. And I guess everyone is so thrilled to be sponsoring things that we only had one small business sponsor. These are at a lower level, but everyone wanted to really chip in and be generous this year. So our last sponsor is Intrinsic. So. Thank you to all of them, and you'll find some of these sponsors will have tables outside where we will have our coffee breaks and poster sessions. Okay, so today's program is going to be, as shown here, as follows. We'll have a session of long talks. We'll have spotlight talks. These short talks will come up next. We'll have our first keynote by Raquel Urtasun. After that, we'll have a lunch break, long talks, Henny Edmoni with her early career spotlight, another set of spotlight talks, and then a poster session, which will just be outside over to the, well, my right of the conference, your left. Afterwards, we'll have a welcome reception, which will be back in this conference center with food and drink served. A couple of notes for presenters. Please come up near the beginning of your session so that you can introduce yourself to your session chair. They know that you're actually here. Also for those of you who are setting up posters, you will set up your posters out in the hallway after the coffee break. We do have RSS Pioneers. By the way, for those of you who don't know, RSS Pioneers is an RSS affiliated event which has some of our youngest, our bright young minds that in robotics come together and share their experiences with the robotics community and the kind of academic field. So they are going to have their posters up in the early coffee break sessions. Then they will take their posters down, and then those of you who have main conference posters will then set up, and then you can leave those there through lunch and so on. So another thing about your presentations, for those of you doing short talk presentations, you should please come up here to the front row. This will be the kind of speakers area over here. You'll come up one by one onto your stage. Onto the stage, we'll play your video, and then you'll go ahead and sit down. Please then sit down until the end of your group. We have 4 or 5 sessions per papers per group. Then those 4 or 5 speakers will then come on stage, and then you'll have a group Q&A session. All right. If you have any questions about this procedure, please come and find me during a break. And after the first couple of sessions, hopefully we'll all get the drill. Okay. Matei, I'd like to introduce our local arrangements chair, Matei Ciocarlie, who will talk to you a bit about kind of last-minute information.
All right, good morning. Welcome to Columbia University's campus. Welcome to New York. We're super happy to have you here today. So just a couple of quick notes. Kris already hit all the key points. You all got an email this morning with a bunch of administrative things, T-shirts and QR codes for the banquet and all of those things. Please read that email carefully because it has important information. In addition to that, there's a couple of things I can mention. So first of all, we do take the mask policy very seriously. So please, when you're in here, unless you're actively taking a sip, please wear the mask and wear it properly. I will come and look at you if you don't, and if you still don't, then I'm going to get Kris, and you don't want that happening. So please take the mask seriously. We have plenty of space. Also, if you look behind you and up there, you see that beautiful VIP section? That's actually open for everybody, okay? So to get there, to get to the balcony, there's an elevator or a set of stairs, kind of at that corner, outside the auditorium in that corner. Take the elevator to the 2nd floor, and then immediately you'll find the entrance to the balcony. So please use the balcony. In total, we have about 1,100 seats, and we should have at most 550, 600 people in the room. So there's place to spread out. Especially right now, there's nobody at the balcony, so if you really are, from a pandemic perspective, you want your space, go to the balcony, and right now you have it all to yourself. Okay, what else? For the banquet tomorrow, the 2 things that I'm going to be stressing again and again. Your QR code on the back of your badge is your ticket to board the cruise. It's a yacht, a boat cruise. If you don't have the badge with the QR code, you won't be able to get on it. So please be sure you have your badge. Anybody who registered before Monday 10 a.m. should have a QR code. If you registered before Monday 10 a.m. and for some reason you don't, come see us at the registration desk. Then I'm going to say this today and again tomorrow. Boarding is at 6:30, the boat leaves at 7. And it's a boat. Once it's gone, it's gone. There's no more getting back on. So make sure you get there on time. For the banquet, for the boat cruise, we have a small number of additional tickets available. Some of you have been emailing us the last couple of days asking if you can bring one more person to the banquet, and I've been saying no so far, but it turns out that we can. So Florian, our registration chair, who, by the way, has done an incredible job shouldering all the registration load for this conference, he's made available a number of registration tickets for the banquet through the same RSS feed loop registration procedure you went through to register for the conference. Okay? We don't have that many of them. They cost $150. So first come, first serve. If we get more available, we'll open up more of those. But now is the time to go get them. Then also for the lab tours on Thursday, registration is actually also going to be through the same procedure. So go to the RSS website, click register. It'll take you to the feed loop website, and that's where you can sign up for lab tours during lunch break on Thursday. And we will have lunch for lab tour attendees, and you're going to see Shuran's lab, Hod Lipson, Sunil Agrawal's lab, and my own lab. So that's what's going to be happening on Thursday. Okay, for lunch, just go out on Broadway, make a left. This general area, 116th to 110th, has plenty of restaurants, and there's many more. Just check the email that you got this morning. And other than that, you know, enjoy the conference and enjoy the city. Welcome.
Okay, so the chair of our first session is Christopher Heckman from the University of Colorado.
All right, thank you for coming to the first session, making it out here, even though I'm sure many of you had a good night last night. So the first talk today is going to be ACID, Action-Conditional Implicit Visual Dynamics for Deformable Object Manipulation. You can come on up and set up. It's going to be presented by Zhenyu Jiang.
Can I switch?
You're on.
Yeah, great. Hopefully it should work.
Do you have audio?
No, I don't.
Do you have audio?
No. Oh, great. Okay. So, hi everyone. I'm Zhenyu Jiang from UT Austin. I'm glad to present our work, ACID, Action-Conditional Implicit Visual Dynamics for Deformable Object Manipulation. This is a joint work with collaborators from Stanford, NVIDIA, and Caltech. From playing with plush toys to making pizza dough, deformable objects are prevalent in many daily activities. Perceiving these objects and modeling their dynamics play an integral role in building autonomous robots to interact with these soft objects. Decades of robotic research have developed algorithms for manipulating non-rigid objects. Such methods have shown success in deformable linear objects, cloth and fabric, and some simple primitive 3D shapes. However, modeling general volumetric deformable objects is still beyond reach. Two major challenges of modeling realistic volumetric deformable objects are partial observability and the complex nonlinear dynamics. Deformation can induce severe self-occlusion and make certain parts invisible. In addition, the complex nonlinear dynamics in the infinite configuration space of these deformable objects make the problem even harder. In this project, we study the goal-conditioned volumetric deformable manipulation. Given a start and a goal state observation of a deformable object, we learn a visual dynamics model. With the learned visual dynamics model, we use a model-based control to roll out multiple actions that manipulate the object into the goal state. To tackle the challenges of partial observability and nonlinear dynamics, we introduce ACID, Action-Conditional Implicit Dynamics. ACID takes as input the RGBD observation and the action and predicts geometry and dynamics of the object. It reconstructs 3D shape from partial view and predicts action-conditional forward dynamics. The key idea of ACID is using neural-implicit representations to jointly represent the geometry and dynamics. Neural-implicit representations are mappings from a 3D coordinate to quantities at the coordinate. It serves as a unified representation for geometry and dynamics. It's continuous and memory efficient, and it can be end-to-end trainable with multiple supervisions. We use neural-implicit representations for occupancy, correspondence, and flow fields. Occupancy field is a mapping from a 3D coordinate to the occupancy value, whether the point is occupied by the object. It encodes the geometry in the neural-implicit representation. We encode the dynamics in the correspondence field and the flow field. The correspondence field contains the local feature descriptor. It is useful when comparing the predicted deformed shape and the goal object. The flow field contains the per point flow vector, which describes the deformation. Our model, ACID, predicts occupancy field and correspondence field from RGBD observation. ACID also predicts the action-conditional flow field. We represent the action as a 3D grasp point and a 3D release point. We introduce our occupancy and correspondence prediction here. We first back-project the RGBD observation into RGB point cloud. Then we encode and project the point cloud into 2D feature planes. To enhance fine-grained reasoning, we use local implicit representations. Given an arbitrary 3D location, we use bilinear interpolation to query local feature at this location. Our decoder predicts occupancy score and per point feature, given the 3D location and the local feature. The occupancy decoder predicts the occupancy field, and the correspondence decoder predicts the correspondence field. We can supervise the occupancy decoder with the ground truth occupancy. To train the correspondence decoder, we need to specify the correspondence across frames. The object is under deformation across frames, so we need deformation invariant metric to determine if a pair of points are corresponded. We employ geodesic distance, the shortest distance between 2 points on surface. For example, the purple pair of points are not corresponded, so the geodesic distance between them is large, although the Euclidean distance is small. The geodesic distance between the green pair of points is small, and these 2 points are corresponded. So we use the green pair as positive pair and the purple pair as negative pair. We use contrastive loss to pull the point features of positive pairs close and push away the point features of negative pairs. With geodesic-based contrastive loss, our model can predict deformation-consistent point features to establish correspondence. Then I'll introduce our dynamics prediction branch. As presented above, we extract 2D feature planes for occupancy and correspondence field prediction. To predict dynamics from single observation, we use action as an extra input. We combine the back-projected point cloud with the action parameters and use the dynamic encoders to project and encode them into another set of 2D feature planes. Conditioning on both sets of feature planes, our flow decoder predicts the action-conditional flow field. In conclusion, our model ACID takes as input an RGBD observation and the action represented as a grasp point and a release point, and simultaneously predicts occupancy field, correspondence field, and the action-conditional flow field. To generate training data and evaluate our method, we develop a new framework, PlushSim, for volumetric deformable object manipulation. PlushSim is a simulation framework with GPU-accelerated FEM simulation and real-time ray tracing. It provides realistic dynamics modeling and observations. We generate our dataset with PlushSim, we randomize lighting and scene layouts and manipulation actions, and altogether, we get over 17,000 of manipulation trajectories. We split the trajectories into train and test set by objects, so we train and test ACID on different objects. We apply model-based manipulation with ACID as a visual dynamics model. We sample action sequences with ACID's occupancy field. And given the action, we use flow field to predict the object shape after deformation and compute the distance between the predicted shape and the target shape with the correspondence field. And we select the best action based on the distance. We quantitatively evaluate the goal condition manipulation performance of ACID and other baselines. First, we evaluate the pixel flow, which models the visual dynamics in 2D pixel space. Pixel flow predicts incorrect flow direction and shows very poor manipulation performance. It indicates that modeling deformable object dynamics requires reasoning over complete 3D object shape. We also evaluate voxel flow, a voxel-based action-conditional visual dynamics model. The voxel representation is discrete and gives noisy and inconsistent flow prediction. This suggests the need of a continuous representation when modeling deformable objects and their dynamics. Benefit from the continuous and compact neural implicit representations, ACID can predict consistent and smooth action-conditional flow. In addition, these results are on unseen test object. ACID can generalize learned visual dynamics to unseen objects. We also conduct a self-ablation, where we replace the geodesic-based contrastive loss with the Euclidean-based one. With geodesic-based contrastive learning, ACID can establish more accurate correspondence between the predicted and target objects, which boosts the performance of goal-conditioned manipulation. Here we show the qualitative results of manipulation in simulation. ACID can predict consistent correspondence field across the frames. We also apply ACID to real-world deformable objects. Trained with simulated dynamics, ACID-based model predictive control can generalize to real-world observations and successfully manipulate the object into target configuration. We tried some other deformable objects and configurations, benefited from the randomized training data and multi-step property of the model-based manipulation. ACID can generalize to objects with different appearances and configuration and dynamics. In conclusion, we propose ACID, which encodes the geometry and dynamics of deformable objects in structured neural implicit representations. To train ACID, we developed PlushSim, an open-source real-time FEM simulation framework for volumetric deformable manipulation. We deploy ACID both in simulation and on the real robot and show successful.
Something that was not what was the right behavior for the object.
Okay. So basically the question is where our method does not work, right? Yeah, so it's a good question. So so as I said, we do not explicit model physics from observation. So that means when the dynamics of the object does not align with the one in the simulation, it does not work. For example, you have those not so compliant object that has some elastic property. So it will go back if you grasp a little bit away, and then it does not work because it's not the same as in the simulation where we train our model. That's a major limitation. Sorry, can you speak a little bit louder? I cannot hear.
Okay. Anyway, great talk.
Thank you.
I just have one question. So if I understand right, you project the object into the XYZ planes. Why is that beneficial compared to reasoning directly in 3D space?
I see. So the question is why do we project the point cloud into XYZ planes? Is that correct?
That's
okay.
right.
Cool. That's a good question. So basically we would refer to the convolutional occupancy network, which is a previous work using implicit neural representations. And the main reason we are doing this projection is because it greatly reduces the computation cost. If we directly do everything in the 3D space, then the memory cost will be huge, and basically GPU would explode.
Great, thanks.
Yeah, please.
Yeah, I just have a quick question regarding geodesic distance. Can you elaborate a little bit more on what point are you calculating the geodesic distance with respect to? Thank you.
Sorry, can you repeat the question?
Yeah, can you just elaborate a bit more on how you use geodesic distance to establish the correspondences across two targets?
I see. Yeah. So that's a good question. So the question is, how do we use geodesic distance to establish correspondence? So we use geodesic distance as a contrastive loss. So basically, we use geodesic distance to define which pair of points are corresponded. So with the geodesic distance metric, we can use this contrastive loss to pull close the 2 points which are corresponded. The point features of a pair of points are corresponded and push away the point features of pair of points are not corresponded. So at the end of the day, we're just learn an embedding field, and this embedding field is consistent across the deformation. Yeah, so it's geodesic distance serves more as a loss or a metric to learn the feature embedding.
Okay. So my question is regarding generalization. So have you tried it on objects that are unseen during the simulation training?
For sure. Yeah. Basically, all the real objects are not seen during the simulation training. We can't find the same object in the simulation and the real world. Yeah.
So in that case, the correspondence is kind of generalized to novel objects.
Yeah. So basically, even during the simulation training, we train on different objects and test on different objects. So the learned visual dynamics and the correspondence can generalize to different objects.
The fantastic talk. For this work, you are focused on volumetric deformable object, but it looks like given observation, you can only see the surface points. And also, I'm not familiar with how geodesic distance is defined, let's say, inside the volumetric 3D object. Could you elaborate more on that? So are we only estimating the dynamics over the visual appearance of outer shell or the entire volumetric object?
Okay, great. That's a good question. So the question is since during when capturing the observation of the volumetric deformable object, we only capture the surface. And how do we define the geodesic distance like between like a pair of points like inside the object? So, so basically first we have an occupancy field where we do 3D reconstruction. And using that 3D reconstruction, we can find the surface point. And then we can like compute geodesic distance on the surface point. So at the end of the day, we'll still like compute the embeddings on the surface point, but the complete surface points instead of like partial observations directly captured.
Thank you.
No problem.
I think that's great. So let's thank our speaker again. Thanks, Renyu.
Thank you.
All right, the second and final speaker of the session will be Graham Best. As he's setting up, I'll introduce his title. It's Resilient Multi-Sensor Exploration of Multifarious Environments with a Team of Aerial Robots.
Good? Okay, ready? No. Okay, good morning, everyone. So my name's Graham. I'm going to be presenting our work on aerial autonomy. So this work was done at Carnegie Mellon University, Oregon State University, and I've recently moved to University of Technology, Sydney. So what we're pushing in this work is this idea of resilient autonomy in multifarious environments, where multifarious means many and varied environments. No? Is it this chord? No, I'll try not to touch it. Yeah, don't touch anything. Yeah, so as I was saying, so what we're pushing in this work is resilient autonomy in multifarious environments, where multifarious means many and varied environments. And so this is where we have lots of different challenges in the environments that we don't know ahead of time. So this can include things such as narrow passages. So my video's not working. Here we go. So this can include narrow passages, such as in this cave here, large, expansive open environments, complex topology environments, such as weaving through beams in the ceiling and narrow passages, things like stairwells and vertical shafts, and areas with challenging perception, such as through gas and smoke. And so what we're really pushing this work is trying to get autonomy that works across all these environments. So every picture that you see here is all running the exactly same code, as well as the examples that I'll present later. So our contributions are along 4 fronts. So firstly, we address this problem of multi-robot, multi-sensor exploration and coverage, which I'll define a bit more in a second. We want this exploration to be resilient across a number of environments, as discussed in the previous slide. We want full autonomy from takeoff to landing without a human in the loop. And we present lots of experiments with physical robots moving at high speeds in environments over the scale of kilometers. All our code has been released and open sourced. So this problem, what we're really pushing is this idea of system level performance, which is quite hard to define formally. But our primary objective is this first point here. We're trying to maximize this exploration and coverage objective. And so what I mean by this is we have a secondary objective, which is a LiDAR, which discovers the geometry of the world. Then what we're actually interested in is observing all these surfaces with cameras at close range. Then there are lots of other system-level objectives, such as land safely at the takeoff location. We want to respond appropriately to unforeseen challenges. And we want multi-robot coordination, particularly decentralized, in environments where the communication is unpredictable. So what I'm presenting here is the system, as you see in this picture here. And I'm just going to very briefly talk about each one of these components in this talk. So let's start with the behavior executive. So it's responsible for the very high-level decisions and switch between what behavior should be happening at any point in time. And so we represent this in the form of a behavior tree shown here. Put simply, behavior tree is a logic structure. It takes in these various conditions, which are true or false, and at any point in time, it tells you which action should be taking place right now. In this example here, the behavior trees are read from left to right. We have these diagnostics, everything's currently okay. We successfully take off, and then currently we're in this expiration phase where there's various variants of this expiration that can be selected between based on changes in the environment. And then later on in the mission, we have the landing sequence, which will get us safely back to home. So next component is this map processor. So it's responsible for taking in the SLAM output and then forming different mapping products that are used by the different planners. So there's three main types of mapping products. So the first is these expiration maps. For this, we use an open V2B structure. It's similar to an octa map, which you might be more familiar with, but it has certain benefits. And what we use this for is representing what has been observed by the cameras and LiDAR. This is shared across the team of robots. In the middle, we have a navigation roadmap. This keeps track of where we've been, how to get back to places. It accounts for repairs. If, for example, if a door shuts, it will fix that. This is also shared across the team. And lastly, on the right, we have local planner maps, which is represented as a distance transform map. We include dust filtering, and the local planner is computed on the GPU. So next up, talk about the global planner, but particularly the exploration component of that. So we use a frontier-based exploration where we use two different types of frontiers for those two different objectives I talked about. Viewpoint extraction, we then rank these viewpoints according to a series of heuristics, then form an RT planner to get to these viewpoints. Coordination is achieved by sharing two types of information. Left-hand side, you see shared exploration maps. On the right-hand side, we see shared navigation roadmaps. And these two communicated bits of information will influence both the frontier selection and as well as long-term navigation in particular parts of the mission. And so these two ideas are relatively simple, but together they came together to achieve very good coordination across very large-scale environments. So local planner, so it consists of three main components. So first is we perform an A-star search over the distance transform map, and it actually pushes things away from obstacles to improve safety. That trajectory is matched to a dynamically feasible trajectory library in the middle. And then we perform speed and yaw control to get through narrow passages, such as doorways, and I'll show you a video of that in a minute. Lastly, which I just briefly mentioned, the controller, we have an onboard Bixhawk flight controller, which I won't talk about here. So we formed a huge amount of experiments across a wide range of caves, mines, indoor structures, etc., as well as we performed in the DARPA Subterranean Challenge. These experiments were performed with our custom drones shown in the middle here, roughly 70 centimeter diameter, onboard sensing, computation, etc., roughly 10 to 15 minute flight time. Okay, so I'll show you a video here of just a few different clips of examples of particular behaviors. So this particular shot is from the final competition, the DARPA competition. And you can see it's able to reach areas of the course that our ground robots couldn't reach. So there's actually things hiding up there that we scored points for. So here's an example of going through a doorway. This is also in the competition. So the exploration decided that it would be worth going through that doorway. Local planner then lines up the robot to squeeze through without bumping into things. And then our autonomy adapts, so then it might go through that doorway into a wide open area. And in these wide open areas, then the speed increases up to about 3 meters per second. So yeah, this is an example of a map that gets built up here. This is Laurel Caverns. This is an environment that we went to back to quite a lot. It was interesting because you see there's a very complex kind of geometry which makes the mapping, particularly the frontier generation, quite complicated. And this is another complex topology environment. So here we're weaving between different beams in the ceiling. The exploration's found this hole in the ceiling, and the local planner figures out how to get through it. It squeezes through there. And once it's through there, then it opens up into this vast other room that it then goes and explores. So this, jumping forward in time a bit, you can see here it's weaving between different beams in the ceiling, drops down vertically. And then once it reaches this more open area, then the speed will pick up since there's much wider safety tolerance. And so the last example here is stairwells. One particular challenge here is we're actually going down but below the blind spot of the velodyne. So you're actually going in an area that you can't see. And so it took a lot of tuning to try to get that right, because it is actually quite hazardous since you're going through blind. So we had lots of other results. Some of these are summarized in the paper, but a few quick kind of takeaway messages. So in expansive environments, we had environments where robots were exploring over 1 kilometer per robot, moving at speeds up to 3 meters per second. This was contrast to very kind of tight, narrow passages type environments where the speed slowed down and the autonomy adapted to that. Then there was lots of complex environments where there's kind of a mix of these different things and the autonomy had to adapt. Lots of examples of resilient behavior, such as emergency landing if we run out of battery unexpectedly, road map repair if, for example, a door shuts or something like that, then there's other ways to navigate. So we also competed in sub-T finals. We had 3 aerial robots flying in the final competition. Our aerial robots found 8 artifacts in the course. But also part of the sub-T competition, they were coordinating with ground robots, which I'm not going to talk about in this paper. So lots of lessons learned from this set of experiments. I think one particular challenge was avoid overfit into one particular environment. So we're trying to generalize so that we can go to any new environment and make it work there. Balancing solution complexity is complicated. So some parts of our solution are very theoretically interesting, whereas other parts are kind of quick hacks, and trying to balance those two was quite challenging. Multi-objective exploration, also challenging. How do you balance between these different things? And resiliency, we achieved this through redundancy, and we found that particularly that the behavior tree structure was a good way of representing that redundancy. So lots of areas for future work, ongoing projects. I won't talk about all these, but I'd particularly like to point out our code release. Encourage you to go look at that. And yeah, thanks for listening. We'd also like to thank DARPA for sponsoring this work. Come and have a chat in Poster 2, and I think we have time for questions.
Excellent, very cool talk, thank you. While we're waiting for other questions to populate, I guess I'll start with one. I saw that you did a marsupial configuration. How did you, I have just a few questions about that. How did you determine when to launch off? It seems like a classifier for that would be pretty challenging to create, but I'm curious how you did it. The second thing is that when the UGV is exploring into the environment, it's obviously collecting state data. Is that what you give to the UGV when it starts to launch off, or are you collecting information and processing state estimations and mapping as you, with the robot on in the marsupial configuration? Curious about some mechanics there.
Yeah, so a bit of context there. So in the sub-T challenge, we had ground robots and aerial robots. And so the aerial robots, some of them took off from the start location. Others were carried into the environment from the ground robots and took off somewhere else. And the question there was about, so how do you know when and where to take off? My short answer is in the competition, that was all done by the human operator. So that was kind of a very high-level decision. That was kind of one-off thing that didn't take too much effort from the human operator. But we'll add to that, it's kind of a research area that we have been looking to outside of this paper and this competition. We did actually write a paper on it last year, I think, at ICRA. And we're looking at how do you actually reason over what you might see if you were to take off at this location. Yeah, so it's not in this paper, but we can talk about that too. Yeah, and then apart from, so when we take off from the ground robots, it does, if I remember correctly, the aerial robot's actually turned off until it gets to the takeoff location. Then just before it takes off, that's when it shares maps. And then, so then the aerial robot can then actually use those maps to explore things that the ground robot hasn't seen. And there is some information, if you're in communication range, there is information shared. In this paper, we typically talk between the aerial robots, but also the ground robots have a role there too.
Let's start with the stage right, so audience left.
Hi, Graham. First, this is really, really great work. I'm really excited to see robots operating in complex cave environments, and large spaces, and very narrow spaces as well. What I wanted to ask about was, like, from a systems perspective, and you mentioned, like, there's some hacks, and you build these things incrementally based on time available and whoever you have on the team. So given that, what would you like to change, or are there things that you wish you'd done differently? And what comes next?
Not sure if I quite got the question, but what would do differently? I think, so this project was going for about 3 years or so, and so I think over those 3 years, the system naturally evolved over those 3 years. And I think we particularly, our design process came really motivated by the experiments. So we were going out testing almost every day, and then we'd come home and look at the data and adapt each time. Yes, so I'm not sure if there's any clear changes I'd make to this exactly as is, because that was kind of as presented in the competition. I think looking forward, though, I think it kind of depends on the context. So I'm trying to look more from the research side now. So from the systems perspective, I think we presented something that worked well for competition. I think some research challenges is trying to bring, for example, learning into some of the components. So maybe if I go back to that. I think this is the slide I was looking for. Yeah, so particularly trying to bring learning kind of new algorithms into the components. For example, the selection heuristic for the frontiers, for example. I think that was something we're kind of constantly fiddling with, and if there was a more general solution to that, then that's something we'd be interested in. Yeah, I'm not sure if that answers your question, but we can talk more in the poster session.
Yes, please, but thanks a bunch.
Thank you.
Yeah, thank you for the talk. I just have a quick question regarding, I think, your local map. I think you mentioned your local map is on the GPU. How large is the map, and do you transfer it to CPU for planning, or if you do so, how does that affect the latency of the system? Thank you.
Yes, so the GPU map, I think it was roughly 8-meter rectangle around the robot. And I think it was a voxel type representation. I can't remember the exact resolution, might have been 10 centimeter voxels. I can't remember the exact latency, but yes, so it is computed on the GPU, then transferred to the CPU for planning. So the planning is not done on the GPU. Yeah, I don't have like specific numbers on that latency though, but we found that that was not an issue, but I don't have specific numbers to quote for you.
Okay, thank you, Best. I'm really interested in your work. Coming from my own background, from Africa, I'm just wondering, did you consider environments such as farm environment or wildlife environment, and how well will it perform in this environment?
Yeah, so we're particularly motivated by environments that were in the DARPA challenge. And so that included caves, urban structures, and tunnels. Thank you. But more broadly, yes, all this stuff can work above ground as well. I think one particular challenge that we see underground is that there's a lot of narrow areas that you might not have if you go out on a farm, for example. The other big challenge is we don't have GPS underground compared to if you're above ground, that might simplify things in terms of localization. So in the underground context, that means that SLAM also had to be running on this one computer that was on the robot, and so that took up basically half the computer, and that really limited certain things. If we didn't have SLAM taking up most of the CPU, or a reasonable percentage of the CPU, then I think there's probably more planning that we could do in other contexts.
We'll take one last question.
Thank you. This is really interesting work. I had a question about if you have a team of multiple robots, how did you handle discrepancies between, say, one robot seeing something and another robot seeing something conflicting? For example, things like mirrors or glass tend to cause problems for VIO or LiDARs. How did you handle these discrepancies that a team of robots might see?
Yeah, so if the two maps end up being different and shared, right, I'd say the first answer there are certain decisions that are only use my own map, and so that means if a different robot sends information that has errors in it, then most of the decisions are not affected by that, since I'm just using my own map, and I'm assuming my own map is correct. There are certain behaviors where, particularly when the roadmaps are shared, so if one robot says, go to somewhere very far away, and we use a roadmap to get there, one thing that came up, for example, if there's some kind of SLAM drift, then that roadmap might not line up properly, for example. There is kind of low-level redundancy in terms of the local planner and whatever to kind of get around that issue. But I agree it's a challenging problem there.
Thank you. Yeah. All right, let's thank Graham again.
All right, thank you for our two guinea pig speakers for all of our AV issues. For those of you who are not watching in person and online, apologies for all of our virtual streaming issues. So it's doubly hard to run a hybrid conference, who knew? All right, so we have now a coffee break until 10:30. Oh, by the way, I wanted to say one thing. For those of you who are presenting, it's actually helpful if you're to remove your mask during speaking. For those of us who are hearing impaired, seeing lips actually helps comprehension quite a bit. So if you're not comfortable with removing your mask, that's fine. But if for those of you who are, please try to remove your mask while speaking. All right, thank you, and I'll see you all in half an hour. Coffee break.